Hi everyone, and welcome to the PET SPECT lecture. So PET stands for positron emission tomography, and SPECT is single photon emission computed tomography. And so with the tomography in its name, you know that this is a slice or a 3D capabilities of this. So before we get into this, a little bit more nomenclature. Should have done this with the MRI, but there are different planes to imaging. So the axial or transverse plane slices someone in half, not across this plane. And so this is what that image would look like, going up and down the body with the vertebrate always down at the bottom of the screen. The coronal plane goes from front to back. And you can see it in this image right here where you can see the heart. And then the sagittal plane goes from side to side. And so again, with the spine to the right, you can see this in the very last image. So those are the three planes of imaging. So MR and CT we've seen provide anatomic images. There are contrast agents from them, but they mostly are used in the clinic for anatomical contrast. So what information would you get from PET and SPECT? Well, PET and SPECT both require a contrast agent. They use gamma rays, and we will get into that. But there are no gamma rays in the body, and so you always need a contrast agent. This is unlike the MRI and the CT or ultrasound, where anatomy will generate the contrast. And so positron emission tomography, it measures regional tissue functions in vivo. So you can get blood flow, which is perfusion, blood volume, vascularity, oxygen utilization, glucose metabolism, pre and post synaptic receptor density and affinity, neurotransmitter release, enzyme activity, drug delivery and uptake, gene expression. So you can get all of that information. It's a molecular imaging technique. However, you must have a contrast agent that will tell you all of those different things. It's very accurate and very sensitive. So sensitive means that you can see something very small. And why is that? Well, it's the physics of how positron emission tomography works. So you have to make a tracer. It's labeled with the positron emitting radionuclide. You place the subject in the field of the gamma ray detectors, and so this is the PET scanner. The radionuclide in the body will decay. The positrons, and in this case, positrons will annihilate, or the radioisotope will annihilate. It will emit a positron, and it will emit them in a 180-degree linear pattern. And so the positron scatters in tissue, it loses energy. That's your attenuation. And so here's your positron. It annihilates, and when it annihilates, you have a release of a photon at 511 kiloelectron volts, always 511, at 180 degrees at the same time. And so this is why this is very sensitive, because only photons that are coincident, it's called, that 180 degrees hitting the detectors in equal and opposite directions, will it be picked up by the detectors, and will it be used in the algorithm? So very important key factors. Coincident photons are released, and coincident photons are released, and they're both at the same photon, 511 kiloelectron volts. And that is a property of all positron emitters. So F18 is the most common one, or fluorine 18. There's iodine 123, zirconium, gallium, but all of them emit at the same time. So you cannot use two different of these positron emitting isotopes and look at two different things. You can only look at one thing at a time. So the resulting positron, so getting back to our diagram, the radionuclide in the tracer decays, so this is what's wherever it is in the body. The resulting positrons will travel about 1 millimeter in body, then they'll collide with the electrons, they annihilate on contact. Each annihilation will equal 2 times 511 electron volt gamma rays. The photons, again, are traveling in opposite directions. The two detectors register 2 photons at the same time. That's the coincident event. Coincident events are stored as arrays that project through the patient's body, and then the arrays can be reconstructed into tomographic image. So positron emission tomography is a type of radioactive decay where a proton in a radionuclide nucleus is converted to a neutron. It releases a positron and an electron neutrino. A radionuclide is an atom with an unstable nucleus. Neutrino is similar to an electron but no net charge. These are gamma rays, and they have high frequency electromagnetic radiation, so they can penetrate pretty quickly. Commonly used isotopes and their half-lives are carbon-11. This is very quick, 20.3 minutes. 13 nitrogen, 9.97 minutes. 15 oxygen, 2.03 minutes. And 18 fluorine, 109.8 minutes. It is absolutely essential that if you are going to use PET for any kind of imaging, that you pair the correct radionuclide half-life of the isotope with your biodistribution. So if you choose a C11, so carbon 11, and your blood half-life is 18 hours before your particle clears, your particle will be mostly in the blood when the half-life is already gone for the carbon 11. And in general, after 5 half-lives, you can no longer detect the isotope. And so for bigger things like an antibody or for a nanoparticle, you should use zirconium. These things are just too short in order to be able to see them. So here's our electromagnetic spectrum. Radio waves 10 to the 4, 10 to the 2. Microwave, infrared 10 to the minus 2. Visible light is 10 to the minus 5. Ultraviolet 10 to the minus 6. X-rays are 10 to the minus 8. That is what is the CT. And then the gamma ray, your wavelength is 10 to the minus 10 to 10 to the minus 12. So that's an atomic nuclei. So this enables the highly sensitive detection of these particles. So a photon is a particle representing a quantum of electromagnetic radiation, and a quantum is discrete quantity of energy with magnitude proportional to the frequency of radiation it represents. So how can you imagine PET being used in nanomedicine? So take about 5 minutes, write down what you're thinking in terms of how you can imagine PET being used in nanomedicine. Now that you've thought about it, let's see how many of these that you have been able to list. And so one is to label up your polymeric nanoparticles or any kind of nanoparticles with a PET tracer. Again, you have to use the same, you have to make sure that you marry your half-life to the particle pharmacokinetics. And so if you label this with a PET tracer, you'd be able to image, which allows you to quantitate, and PET is quantitative. So you'd be able to image exactly where your nanoparticle is going and quantitate how much is there. And then you'd also be able to keep track of its biodistribution and get percent injected dose per gram. And if you know how much drug was loaded into these nanoparticles, then you would be able to calculate how much drug actually reached the tissue, as opposed to just guessing based on the blood profile and the pharmacokinetic mathematical algorithms that we've talked about. So in this particular example, we were able to not only image, so doing the PET imaging in the ABCD, this is a nanoparticle, so the majority of it will go into the liver. And then the percent injected dose per gram, that you can see that there's a lot of it in the spleen, some in the kidney, a lot in the liver, and a lot in the blood. So again, this gives you exact knowledge of exactly where your radio tracer is. Now, the reason why I say that is because we're tracking the radio tracer, and so if the radio tracer is cleaved in the bloodstream or anywhere else and is released from the nanoparticle, then you're no longer tracking the nanoparticle, you're only tracking the radionuclide. So a lot of studies have to be done ahead of time to see what that cleavage rate is in serum or plasma or whatever, so you can figure out how well intact or how stable the nanoparticle complex is. But it's a pretty decent approximation. Here's another example with a PET dendrimer. Here you can put F18 or iodine. You can see the liver and intestines, the ischemic muscle tissue, and then also the bladder. And so here this is looking at ischemia. Most of these things aren't really done in nanomedicine. Nanomedicine is mostly used to track where, or PET imaging in nanomedicine is mostly used to track where the particles are, and to potentially image things. So being able to image the tumor, because you can get more taken up there. But with everything, there's always a trade-off, and so if there is no if it's staying around in the bloodstream for a long time, then a lot of your organs will get radiated with these radionuclide emitters, and so that's typically not a very good thing. But these can track pH, they can track ischemia, that's the oxygen sensing part. They can track perfusion, so you can look at it and how long it stays in the bloodstream. That can tell you, and you can see with the resolution that you can really tell where these particles are. So it's really sensitive, and it allows you to track where your particles are going. So on the other hand is SPECT, single photon emission tomography. And some people put computed tomography, so there'd be a C, which makes it SPECT. It's like PET, but gamma emitters, it's a single photon. It's not a positron, it's a gamma emitter, it's a single photon. And that means that it's not as sensitive as PET, because in order to do this, you have to be able to decide position. And the only way to do that is to use what's called a collimator, which makes it, and we'll do this in the worksheet, which makes it so that way the photon can only hit the detector at a specific geometry. And using that geometry, you can back calculate exactly where roughly where the photon came from. But that means you have to throw out quite a few of the photons, and so it's not as sensitive. Tech-99 is one of the radioisotopes. Its half-life is about 6 hours. The other isotope is indium-111. This has about a 4-hour half-life. No, 2.8 day half-life. So that is a really good isotope for nanoparticles. The advantages are that there are a lot of SPECT cameras in hospitals. There are about 10 times more SPECT cameras than there are PET detectors in hospitals. And so you have a bigger chance of being able to use it in the different hospitals. And the radionuclides are readily available. They can be shipped from different regions throughout the country. PET, however, because of most of their short half-lives, you have to produce them on site in a cyclotron. And so because of those reasons, SPECT is typically cheaper than PET. Again, its disadvantages, it is less sensitive than PET because of the collimation. There's a difficult attenuation correction because of the unknown path length, and no single photon emitting isotopes of basic biological elements. So labeling with tracer may change biology. So for example, in F18, there are biologic elements with a fluorine, so just substituting out iodine or fluorine doesn't change the biology, you're just using a different isotope. That doesn't happen with SPECT, and so depending on what you're doing, you would have to really make sure that you haven't changed the biology or the affinity or specificity of the tracer. Plus, most of the radionuclides that are compatible for SPECT are usually chelated with macrocyclic or heterocyclic chelators. And so some of these require high heating, 90 degrees Fahrenheit for 10 minutes or 20 minutes in order to open up that chelator and allow that radioisotope to go in and bind. And so if you have a peptide or an antibody, it may not tolerate being heated at such a high level. So your tracer may not be compatible with that. And so SPECT is a little bit more difficult. Also, because it's not conjugated, because it's chelated instead on that chelator, you have an equilibrium between the on and the off state of that radio tracer. So it's more common for the radio tracer or the radionuclide to actually get out of the chelator. And so you'll have free metals that are radioactive throughout the body. But again, with that being said, there are advantages to SPECT. Equipment in the radionuclides are readily available, and it doesn't require very difficult chemistry.